let's consider a function var phi d of x equals e to the d over log x. Now this is a pretty strange function, I'll be honest. It doesn't really appear in a standard real analysis course, even a pre-calculus course, or even a calculus course. It mostly goes unnoticed, but it does have some remarkable properties. The Taylor series at x equals 1 is 0. The function is not. And we have a bump function factor in disguise. So what we're going to do here is first switch the seal off and consider this integral. We expand the binomial like so. And we get a gamma function and a sum over binomials, etc. But this is just bookkeeping. Now let's switch on the e to the d over log x factor. So we'll make the substitution x equals e to the negative t. And this is what we get. Now we can expand that left-hand side term into a sum of binomials, coefficients, and we get a nice function here, which we can plot e to the negative pt minus d over t. Now, when we invert about the peak, the right tail lands exactly on the left. So it's a nice sort of symmetry there. And we'll see that on a logarithmic axis, it's simply even. So the exponent was a hyperbolic cosine all along. Now here is Schläfli's integral, which is a nice integral which equals the modified Bessel function of the second kind, k sub nu. And here's our closed form for the one we were looking at. As d tends to 0, we get a nice form involving gamma, the gamma function. And d is a dial. So we get Euler on one end and Bessel at the other. Pretty cool. And there's a special value, c equals 1/2, yields a nice value involving the exponential function. If we sub it in, we recover finite sum of exponentials. And we can do some numerical approximation. Now let's look at one level down, and this is where it gets interesting. The same k, that modified Bessel function, appears on the seed by a different road. A local inversion globalized into a functional equation. So it's pretty interesting because this integral actually does connect back to zeta space.